Okay, so this is the second lecture on invariant subspaces. So let's start with what we have. Just one sec. So invariant subspaces. Okay, so this is the second lecture, right? So let us first recall a few facts regarding diagonalizable operators. Okay, one characterization we had of diagonalizable operators was that um, the algebraic multiplicity of eigenvectors must of eigenvalues must coincide with the geometric multiplicity of them. In other words, we have that the algebraic multiplicity of some eigenvalue eigenvalue C must be equal to the dimension of the eigenspace associated with the eigenvalue C, right? So this must be taking place for all eigenvalue C. So this was the one characterization of diagonalizable operators, because the fact behind this characterization was of this sort, that if so happens, then we can write the vector space V as a direct sum of, or we can just simply use the word sum, or we can also use the word direct sum, because the representation of every element V with respect to the eigenvectors of as in each of the eigenspaces are typically unique. So we can write them in this sort. Let us use it, okay, right? And from here we had the fact that then if I choose the basis elements from each W1, from each Wi, then we will be able to form a basis of V, and that basis of V will be typically serving us to form the matrix representation of the linear operator which we are working with, and the matrix will be a diagonal matrix. So this was some point of view we had uh, in some previous lecture where we discussed these things. Okay. Now we had also discussed a few things regarding what a minimal polynomial of a linear operator is, right? And so it's basically the least degree monic generator of the collection of all annihilating polynomials of the linear operator given. Now suppose you have uh, a diagonal matrix, which you can think of as the matrix representation of a certain linear operator defined on a finite dimensional vector space. So suppose you have a diagonal matrix of this form. So we have C1, C2 till some Cn. Okay, not necessarily the diagonal elements are distinct, but what is the characteristic polynomial? So the characteristic polynomial of this matrix D is surely of this form, right? So it's some x minus C1, x minus C2 till some x minus Cn. Now if we represent this very characteristic polynomial in terms of distinct scalars, so this is of this sort, right? So it's some x minus C upper index we are using, so times some D1, x minus C2 D2, and so on till x minus Ck times Tk. So what will be the characteristic polynomial? So what will be the minimal polynomial? So minimal polynomial is typically the least degree polynomial, monic polynomial, which have roots same as each of these C1, C2 till Cn, and which divides this characteristic polynomial. So it's typically of this form, right? So it's of the form, x minus C1 times x minus C2 and so on till x minus Ck, right? So therefore the roots of the minimal polynomial is typically all the distinct eigenvectors. That is only what we require, and it divides the characteristic polynomial. So this becomes the minimal polynomial. Our goal is to conclude that if the minimal polynomial of a given linear operator or a given matrix is of this form, that it decomposes into linear factors each of degree 1, or I should say each of power 1, then the matrix is diagonalizable as well. To come to this conclusion, we had our first discussion on invariant subspaces, which is in lecture 1. There we discussed what an invariant subspace typically is of a given vector space. So if I just go through a quick recall, so if you have a vector space V over F, so if this is a vector space and T is a linear operator defined on V, then a subspace of V, W, let's say, is called T invariant, if the image of W under T is contained in W. That is, if you choose any element from W, then the image of that element is inside W for all alpha in W, right? So this is the basic definition of what a T invariant subspace is. We had also discussed about some examples regarding this, and we had come to certain conclusions. One more important thing which we had discussed, that what the T conductor of some element alpha is defined as. So if I just again go through a quick recall, so let us just give the definition of what we had said. So let W be an invariant subspace of T and invariant, so it's a T invariant subspace of, say, a vector space V, and let alpha be an element in V. Okay, then the T conductor of alpha into W, defined as, rather I should say denoted as ST alpha W. So it's typically is the collection of all polynomials G which lies in the underlying field F, such that GT of this vector alpha is inside W. Is it clear? So it's called the T conductor of alpha into W. So what will be the T conductor of alpha into the zero subspace, if we talk about? So this is called the T annihilator. This is called the T annihilator of alpha. What are the elements which this set consists of? So it consists of the set of the polynomials G such that GT of alpha is equals to 0, right? Because if it's inside W, then it must be exactly equal to 0. Clear? We have previously talked about annihilators of operators. Here we have something which is called the T annihilator of a vector. Okay. The definition we used in the first lecture on invariant subspace was slightly different. We will obviously come to that. So what happens if W is T invariant? Okay. Observe that. So let me just phrase this as a lemma. Okay. If W is T invariant, okay. So if W is T invariant for T, then W is invariant under G of T, right, for all G belonging to the underlying field. G over the underlying field, right? So this eventually tells us the fact that thus for each alpha in V, S, uh, the set ST alpha W is an ideal of Fx. Is an ideal of Fx. Okay. Obviously, F is the underlying field of the vector space field. Okay, so let's come up with a quick proof of this. The proof is fairly simple because observe that. So you are given that W is T invariant, right? W is T invariant. Therefore, for all elements small w in capital W, T of small w is in W. But that implies T of small w, which is typically T squared of W. This is also in capital W. So if you proceed inductively, then for all R, which are positive integers, T to the power R of W is still inside W, right? So this implies G of T of W is inside capital W for all G belonging to Fx. Because you can just take the linear combination of each of these elements, right? So typically you have W, T of W, T square of W, so on till T to the power R of W, all of these elements in W. So you can just take the linear combination of these elements. So that will again be in W. And that will exactly give you this this very expression, right? G of T of W for a provided polynomial G, right? So it's obvious. It's clear, right? Now you can obviously check that this forms an ideal. I'm leaving that as an exercise. So this is pretty obvious to check. What you need to check is that, so if you remember that if you have a subset I of some ring R, then it forms an ideal if for all AB in I, A minus B is in I, and for all elements from the ring R and small I from capital I, Ri must be in capital I, right? This is indeed the definition of what we call a left ideal, but to ensure that there is no confusion, we can take the ring to be a commutative ring. So if it's a commutative ring, there is no concept of a left multiplication by the ring element or a right multiplication of the ring element. So this can be framed. So there is no concept of a left or right ideal. We can simply define an ideal. That should be typically easy. Okay. So this is the exact fact. Now, to sense that this is an ideal, what are the operations which we typically require? So the operations are also pretty simple to observe that the summation or subtraction of mappings are typically as we used to do, and the multiplication is also pretty obvious. So basic thing is that so f minus g of some t is nothing but ft minus gt, and fg of t is nothing but f of t times g of t. So this is the thing. These are the operations. You can obviously check this out. Okay. So now obviously f of x, or I should say fx, is a PID, right? Because f is a field you have. So that implies, so every ideal is a principal ideal, classical ring theory, right? So it's a principal ideal. So that means there exists a unique monic generator of the set we have, right? Because it's an ideal. Okay. And we name that that monic polynomial to be, say, G. Okay. The G is also termed as, which was the definition we used in the first lecture. G is also termed as the T conductor T conductor of alpha into W. So it's also called the T conductor of alpha into W. And if W is the zero subspace, then G is called the T annihilator. T annihilator of alpha into W. Clear? Okay. Now one obvious thing to notice is that the minimal polynomial is inside this T conductor set, right? So SP of alpha W. So this consists of the minimal polynomial of T, and that is simply because the element 0 is inside W. In fact, every annihilating polynomial is a part of it. So 0 inside W. So if the minimal polynomial of T is say given as P, and G, the T conductor divide, it generates this ideal, so that implies G must divide P. That is the T conductor of some element alpha into W. It must divide the minimal polynomial of that linear operator T. Is it clear? These were certain things which we had discussed in the previous lecture. In this lecture, our first main concern is the concept of what is triangulation of an operator. So, triangulable operator. So, triangulable operator are basically it's very analogous to diagonalizable operators. So, there we used to find operators which can which can have a matrix representation which is a diagonal matrix. In this case, we will consider those operators which can have a matrix representation of a triangular matrix. So, let V be a finite dimensional vector space over a field F. Then T, the linear operator, is said to be triangulable if and only if there exists an ordered basis B of V such that the matrix representation of T with respect to B is a triangular matrix. Okay, so it's quite analogous to diagonalizable operators. Equivalently, we can have a definition for matrices. So let A be a n cos n matrix over a field F. Then A is said to be triangulable if so. What it should be? So A is similar to a triangular matrix, right? So A is similar to a triangular matrix. So that's the basic definition. Okay. So we need to characterize the concept of triangular operators in order to generalize, because obviously observe that any diagonal matrix is a triangular matrix. So having a certain characterization for triangular matrices will obviously give a certain characterization for diagonal matrices. So that's our concern for this lecture, as I said previously. Let's start with it. So to have that characterization, we first need to observe a certain lemma. So a lemma. What we do is that we consider a finite dimensional vector space. So let V be a finite dimensional vector space over a field F. Let T be a linear operator of V such that the minimal polynomial of T, say P, has the following form. Okay, so we are giving a certain form of the minimal polynomial. So it has the following form. So what is the form given? So it's P of x is x minus c1 to the power r1, x minus c2 to the power r2, and so on till x minus ck to the power rk, where each ci is a scalar. Okay. let W be a proper T invariant subspace of V. Okay, let W be a proper T invariant subspace of V. Then there exists a vector alpha in V such that number one, alpha is not in W, and number two, the image of alpha under the linear operator T minus Ci of alpha must be inside W for some eigenvalue C of T. So that is the lemma we have. Let us prove this. Also observe one thing directly from the lemma, that this lemma actually states the fact that the T conductor of alpha into W, of this alpha into W, is basically a linear operator, or rather I should say linear polynomial to be more specific. It's a linear polynomial. So let's prove this. First thing we do is that we choose a vector from V which is not in alpha. We can obviously do that because W is a proper subspace of V. So it's obviously not equal to V. There exists an element which is outside W in V. So let beta belong to V such that beta is not in W. Let G be the T conductor of beta into W. That implies that G must divide P, where P is the minimal polynomial given in the lemma, and then that implies G of X can be written in this form, right? So it can be written as some X minus C1 to the power E1, X minus C2 to the power E2, and so on till X minus Ck to the power Ek. One more thing to observe from the given lemma is that each of the scalars Ci which we have used to define the minimal polynomial are in fact the eigenvalues of T, right? Because we know that the roots of the minimal polynomial are exactly the eigenvalues, right? So G of X has this form because the form of minimal polynomial is given. Okay, and G is also, you need to be concerned about the fact that G is the least degree monic polynomial such that G of T of beta is inside W. So that should be a matter of concern. Now suppose EI is 0 for all I equals to 1 to k. That is, every power is 0, every exponent is 0. So that implies G of T of beta is exactly equal to beta, and that must be inside W because GT of beta is inside W, which is a contradiction, right? Because we have assumed beta to be not in W, which is a contradiction. So since it is a contradiction, so therefore there must be some EI which is not equal to 0. Right? So let EI be greater than 0. But if EI is greater than 0, then that implies X minus Ci, this divides the T conductor of beta into W, right? So that means we can write G of X as X minus Ci times some other polynomial H of X, where H of X is obviously over the field F, and degree of H is less than degree of G, right? So what is G of T of beta? Then what is G of T of beta? So it's exactly equal to T minus Ci, right? H of T beta. Is it clear? Now is HT of beta inside W? Now since degree of H is less than degree of G, and G is the least degree polynomial such that G of T of beta is inside W. Therefore, HT of beta is not inside W. But obviously, HT of beta is inside V. Right? By this exact definition of how HT of beta is basically, right? Therefore, HT of beta, wait a sec. Therefore, HT of beta serves the purpose of alpha given in the lemma. So let alpha be equals to HT of beta. That implies GT of beta, which is equals to T minus CII of HT of beta. But choosing HT of beta as alpha, so we can write it as this. This must be inside W because GT of beta is inside W. So that's the end of the proof, right? Because CI is some eigenvector, is some eigenvalue of T. Right? So this is the exact proof. So using this lemma, we come up with a characterization of triangulable operators. Okay? So we write this as a theorem. What does the theorem say? So let V be a finite dimensional vector space over a field F and let T be a linear operator on V. Okay. Then T is triangulable if and only if the minimal polynomial of T is a product of linear factors, or I should say is a product of linear polynomials over F. Okay. So let's prove this. Now obviously, if T is triangulable, okay. If T is triangulable, then we can find a certain matrix of T which is of this form, right? So it's of the form A11, A22, A33, so on till say ANN. Then you have A12 and so on till A1N. So these elements there, and this part is completely zero. So from this representation, it's quite obvious that what the minimal polynomial will be, right? Because the characteristic polynomial will obviously be of the form x minus a11 into x minus a22 into x minus a33 and so on and so forth. So the minimal polynomial will also be a product of linear polynomials, right? So that implies the minimal polynomial will precisely be a product of linear polynomials with roots with a11, a12 and so on till a1n as the roots. So each diagonal element will actually form the eigenvalues of this linear operator, right? Is it clear? So that's pretty obvious as the roots. Further we can say this in this form. Further, if you can say if the factor say x minus aii appears di times, then the eigenvalue aii equal to some ci has algebraic multiplicity equal to di, right? So it's obvious, right? So we need to prove the if part, that if the minimal polynomial is of this is a product of linear polynomials, then the operator is triangulable. Okay, so let's prove that. Okay, this part. Suppose the minimal polynomial of t, say p, is of the form. So we are giving a certain form. So it's a p of x is x minus c1 to the power r1, x minus c2 to the power r2, and so on till x minus ck to the power rk. Right? Right. Oh. What we do is that we use the previous lemma repeatedly. We start with the zero subspace w. Okay. Let w be equal to 0, zero subspace. Consider a vector alpha 1 in w such that alpha 1 is not in alpha 1 in v such that it's not in w. Then there exists a scalar a11. Obviously a11 is one of these eigenvalues, which is obvious from the previous lemma, that there exists a scalar a11 such that t minus a11I of this value alpha 1 is equals to 0. But that implies t of alpha 1 is equals to a11 times alpha 1. Okay, so this is the first thing. Okay. Now let w1, or we have chosen an element alpha 1, so let this be w1. Okay. Now let w2 be the span of this alpha 1. Let it be a span of alpha 1. Okay. Now is w2 t invariant? Obviously, because observe that alpha 1 serves as an eigenvector. Okay. Because alpha 1 is obviously non-zero since alpha 1 is not in w. So alpha 1 is an eigenvector of t whose eigenvalue is a11, which should, we did not discuss about the eigenvalue, but alpha 1 is surely an eigenvector. So if alpha 1 is an eigenvector, then w2 is an eigenspace because it's the span of alpha 1. So if w2 is an eigenspace, then obviously w2 is t invariant, right? We have discussed this in the previous lecture that eigenspaces are t invariant. Okay. So let alpha 2 belong to V such that alpha 2 is not in W2. Now we had discussed something about linear dependence independence, that if you have a vector which if you have a set S and a vector alpha such that alpha is not in the span of S, then including alpha in the set S makes the it keeps the set to be linearly independent provided that it was already linearly independent. Okay. That is, if S is a linearly independent set and alpha is an element which is not in the linear span of S, then S union alpha is linearly independent. Okay, so this was something we had studied. So since alpha 2 is chosen outside alpha outside W2, so it's not inside the span of alpha 1. So basically alpha 2 and alpha 1 are linearly independent. Right? But again we can use this form, right? So that implies t minus some scalar. Therefore, there exists a scalar, say a22, if f such that t minus a22 I of alpha 2 is equals to some multiple of alpha 1. So let that be a. So a12 alpha 1. Right. So that implies t of alpha 2 can be written as a12 alpha 1 plus a22 alpha 2. Right? Right? Is it clear? So if I proceed inductively, by letting W3 be the span of alpha 1 and alpha 2, we will again find that alpha 3 is t invariant. And then we can obviously again use this very lemma. So using this lemma, we will get some vector alpha 3 3. So let me just put this step for alpha w3. Okay, then w3 is T invariant. I'll ask you to check this as an exercise. Uh, let alpha 3 be a vector in V such that alpha 3 is not in W3. So then that exactly makes the fact that alpha 1, alpha 2 and alpha 3 are again linearly independent. Then there exist scalars, or I should say scalar, say A33 in F such that, one second, yeah, so in F such that T minus A33 I of this vector alpha 3 is some linear combination. So because it's in W3, so it's some linear combination of the elements alpha 1 and alpha 2. So let us view A13 alpha 1 plus A23 alpha 2. Clear? Clear. So from here we can write that T alpha 3 is equals to A13 alpha 1 plus A23 alpha 2 plus A33 alpha 3, and we proceed inductively. Continuing the process, and the process will obviously terminate after some R steps because V is a finite dimensional vector space, and each of these elements alpha 1 and alpha 2 are chosen such that they are uh, linearly independent. So upon reaching the number of elements alpha 1 alpha 2 exactly equal to the dimension of V, the process must terminate, right? So continuing the process for repeatedly. So we get elements alpha 1, alpha 2 till say alpha n. We get the vectors alpha 1, alpha 2 till alpha n such that the representation of each alpha j under T is of this form, right? So it's of this form A1j alpha 1 plus A2j alpha 2 and so on till AJJ alpha j, right? Is it clear? So it continues till only j times, right? So that implies what is the matrix representation of T with respect to, or I should say that what is the coordinate of T alpha j with respect to this basis. Let this basis be V, because this is integer basis, right? Because if the dimension where, let's say, where dimension of V is chosen to be n, because we already know it's finite, so it's a vector of this form, right? So it's of the form A1j, A2j, so on till AJJ, and the rest of the elements are 0, right? So that implies, so if the column vector of, or the coordinate of each of the alpha j's are in this form, then that implies what is the matrix representation of V. So we have the matrix representation of V as exactly the matrices T alpha 1 with respect to B, T alpha 2 with respect to B, and so on till T alpha n with respect to B. So that is precisely this matrix, right? So it's A11, all the elements are 0. Then you have A12, A22, all the rest of the elements are 0. Then you have A13, A23, A33, all the elements are 0, and this process continues. So you have A1n here, you have ANN here, then you have say A2n here, A3n here, and you have a triangular matrix, right? So, which is a triangular matrix. Okay, so I guess this is clear. Okay, an immediate corollary to this theorem is that if you choose a finite dimensional vector space over an algebraically closed field, then that is always similar to a triangular matrix. That is, if, or actually I can say it in this form, that every n cross n matrix over an algebraically closed field, is triangular. And that's obvious from the fact, because if you're an algebraically closed field, then the minimal polynomial will always split into linear polynomials. Hence, you can apply this characterization to obviously conclude the fact that it must be similar to a triangular matrix. I should use the term that is similar to a triangular matrix. Clear? So having discussed a certain characterization of triangular matrix, our next obvious goal is to characterize the concept of a diagonal matrix or a diagonalizable operator with respect to its minimal polynomial. Okay, so our next theorem is obviously our goal. So it says that let V over F be a finite dimensional vector space, and we have T, which is a linear operator. Okay, linear operator only. Then T is diagonalizable if and only if the minimal polynomial of T has the form P of x is equals to x minus c1 times x minus c2 till x minus ck. So it splits into linear factors, right? It splits into linear factors. Clear? Okay. Where c1, c2 till ck are distinct scalars. That's important. Are distinct scalars. Okay. The proof. Now, one thing which we discussed during the start of this lecture was that if a linear operator over a finite dimensional vector space is diagonalizable, then this thing happens obviously. Okay. So we already know that if T is diagonalizable, then this happens. Right? Then this happens. So we need to prove that if T is of this form, if the minimal polynomial is of this form, then T is diagonalizable. So let's come up with that. Okay. Yeah, so this is this part, right? Okay, so let's check. Okay. What we do is that let W be the subspace of the finite dimensional vector space V over F spanned by the characteristic vectors, eigenvectors of T. That is, W is written as W1 plus W2, or we can simply use the simple notation, right? So it's W1 plus W2 plus W3, so on till say Wk, where each Wi is an eigenspace. Okay. Now we know that if this thing happens, that if W is equals to V in this case, then we know that T is diagonalizable. If W equals V, then T is diagonalizable, which was the first characterization we had. So what we do is that we consider that W is not equal to V, and then ultimately we will reach some point of contradiction. So let W be not equal to V. But that means W is a proper subspace of V, right? And since it's a span of eigenvectors, so W is obviously T invariant. Since W is a span of eigenvectors of T precisely, so W is T invariant, right? Moreover, W is a proper subspace of V, because we have assumed that W is not equal to. So it's a proper subspace of V as W is not equal to V. That means we can use the lemma we had proved, right? Right. So there exists some vector alpha in V such that alpha is not in W, and there exists an eigenvalue, say Cj of T, such that T minus Cji of this vector alpha is inside W, right? What we do is that we assume this very vector to be some beta. Let beta be equal to this vector T minus Cji of alpha. Now since W is sum of the eigenspaces and beta is an element of W, that implies there exists elements beta 1, beta 2 till beta k, such that beta I belongs to Wi for each I, such that beta can be written as beta 1 plus beta 2 till beta k, right? Right? Where T of beta I is nothing but Ci beta I, okay, for each I. Okay. Therefore, for all polynomials h over f, what is h of T beta? So it's basically hc1 beta 1, right? So on till h of ck beta k. That this is an immediate conclusion from this, right? And obviously this must be inside W, right? This must be inside W, because this is basically nothing but a linear combination of the elements beta 1 till beta k. Okay. Now by the form given of the minimal polynomial, we know that x minus cj will divide p, right? So we can write px as x minus cj times qx, right? Where qx is in fx and degree of q is less than degree of p. Okay, it's clear, right? Now for any such polynomial q, we can also write that further q of x minus q of cj, this element is also divided by cj, by the factor x minus cj, because if you put x equal to cj here, it becomes 0, right? That is, I'm saying the fact that further if we define a polynomial g of x as q of x minus q of cj, then g of cj equals 0. This implies x minus cj is a factor of g, which implies that q of x minus q of cj can be written as x minus cj times some polynomial h, where h belongs to fx. Clear? Is it? Then what is qt of alpha? Then that implies q of t of alpha minus qcj of alpha. So it's I of alpha, so it's basically alpha itself times alpha. So this is basically equal to t minus cj I of ht of alpha. Right? Now both of these are linear polynomials of t, so they obviously commute, right? So let us go to the next page. So that implies q of t of alpha minus qcj times alpha is equals to ht of t minus cji of alpha. But t minus cji of alpha was chosen to be beta, right? So this is equals to ht of beta, right? Now we had previously concluded the fact that any polynomial you take h from f, ht of beta is inside w. Now ht of beta is inside w, right? It's clear. So that means this is inside w, right? So that implies qt. So we can frame it like this. Let us say it is in this form, that now this is in w, right? Since pt of alpha, which is exactly equal to 0 because p is the minimal polynomial, this is equals to t minus cji of qt of alpha. So that implies qt of alpha must be inside w, but that implies qcj of alpha times alpha is inside w, right? But alpha is not in w, that was our assumption, but alpha is not in w, right? So if alpha is not in w, then that implies qcj must be equal to 0, because the only possibility if that qcj times alpha is in w when alpha is not in w is that this terms become 0, and for this term to become 0, because alpha was also chosen to be a non-zero vector, qcj must be equal to 0. But qcj cannot be equal to 0 because cj is a eigenvalue and p is the least degree polynomial such that cj is a root of it. But since degree of q, or we can just simply say this in this form, we don't need that as well, because if qcj is equals to 0, then that will imply p does not have distinct roots, because p of x was defined to be x minus cj times qx, as p of x was taken to be x minus cj times q of x, which is a contradiction, because p was chosen to have distinct roots by the form of p which was given, which is a contradiction. So that implies, therefore, so the contradiction comes as a result of our initial assumption, which was w is not equal to v. So therefore w must be equal to v, which implies t is diagonalizable, right? Which implies t is diagonalizable. So that's one more characterization we have of diagonalizable linear operator. So one, we had got that the algebraic multiplicity of each of the eigenvalues must be equal to the geometric multiplicity of them, and one more, we got that if the minimal polynomial is a product of distinct linear factors, then again t is diagonalizable. That is one more characterization we have. Okay. So let us end this lecture with a very simple example. One second. Yeah. Okay. So let me find an example. One second. Yeah, this example will do. Okay. So the example is as follows. Every matrix A over R satisfying the relation A squared equal to A is diagonalizable. So what is the solution to this? Now, if A square equal to A, then that implies the minimal polynomial of A, say P, is of the form P of x equals to so it's x times x minus 1, right? So that exactly satisfies the characterization we just discussed, which implies A is similar to a diagonal matrix. The other way of saying that A is diagonalizable. Okay, is it clear? Okay, so yeah, so let's end this lecture here. In the next lecture, we will be starting with the concept of direct sum decomposition. Direct sum decomposition of vector spaces, and we will eventually lead to a very important theorem, which is the primary decomposition theorem. Primary decomposition theorem, which will give us very important matrices, or rather I should say two very important forms of matrices, which are the Jordan canonical form and the rational canonical form. Okay. So more or less we can say about the fact that the detailed conceptual analysis of diagonalizable operators is end by now. Now diagonalization is something which will be of main importance. The more importance is exploring linear operators uh, on a higher basis. Okay. So meet you guys in the next lecture.